Good morning. So we're going to be looking at something called a normal distribution. Now, what we've been doing for the last 2 weeks is the bar chart, right? So things like coin flips and such like that, and we can easily look at the histograms. We can now easily calculate, all the other stuff. So the normal distribution, the idea is this: if I have a set of values, a set of things, and by the way, you're talking gigantical populations of stuff, okay? Gigantical populations, like all human kind of stuff, all dogs. If I'm doing it in a graphing situation, I'm going to go ahead and mute you for a second, Rocco, because it's a lot of background noise. Or unless you can mute yourself, because I'm recording this. If we looked at, for example, human heights, all human beings on planet Earth. If you look at duration of pregnancies for all people who get pregnant, how long is a pregnancy? In other words, whatever the due date is, 1 day early, 2 days late, that sort of thing. If you looked at the duration of pregnancies, there are some things, some naturally occurring phenomena that we know are what we call normally distributed. Normally distributed means literally you see this, the perfect bell-shaped curve. Now, not everything works this way, right? When we talked about the multiple guess test, it didn't look that way, did it? Most of the outcomes came at the beginning, like 0 right, 1 right, 2 right. Do you remember? And it kind of changes. Income doesn't really work this way. We know income, right? There's people always way out here. There's certain things that don't really work this way, but there are many things that work this way. And we say they're normally distributed. And if they are normally or more or less normally distributed, we can make conclusions unbelievably fast and very simple without doing lots of data collection. And that's actually kind of a neat thing. So what we're going to do today is we're not going to do any examples. That's Thursday's class is going to be all examples. Today, we're going to learn how to actually use the tables to look up values and to do the calculations. Because all of the values in the table that I'm showing you are pre-printed, computer-generated stuff. Now, it's a very calculus argument that comes along. So we start with what we call the standard normal distribution. And what the standard normal distribution is, it takes into account only the z-score. Now, a z-score can be positive, it can be negative, it can be 0. Do you remember what a z-score was? The z-score was your score minus the mean over the standard deviation, or it was your score minus the sample mean over the sample standard deviation. Both of these formulas are correct. Right now, we're going to consider that we're working with populations for a moment. So human beings, right? All dogs, things like that. And if we have information, so if I'm above average, my z-score is positive. If I'm below average, my z-score is negative. And in simple English, the z-score is the number of standard deviations above or below the mean you are. Okay, so whatever your score minus the mean is, if you divide it by a standard deviation, you're going to get a number like 1 or 2 or 3 or -1 or -2, probably a decimal value. But that tells you more information than anything else does. And so in this one, we put the y-axis in the middle, and then we say it looks kind of like this. This would be a z-score of 0. And then maybe, this would be 1, this would be -1, 2, -2, and so on. Now, I'd mentioned before that the vast majority of all outcomes happen between -2 and 2. And we're going to actually be able to see that in the tables. So we're not going to calculate today. We're going to read and then do some simple mathematics. Now, here's what makes this so beautiful, this concept. Let me move this. She's out of the way. Hold on. I want to make sure this is centered somewhat. There we go. What makes this particularly beautiful is the mathematics behind this. Now, you don't need to know this. This is actually graduate level calculus kind of stuff. The mathematics behind this is the area under this curve, which goes forever. The area is exactly equal to 1. Now, the reason that's a really cool thing is, what do probabilities have to add up to? 1. So that means in the normal distribution, probability is equal to the area. And area is something we can actually calculate. We can calculate area, even though you're not going to do it by hand. It's done using computer generated. So if I said, what do you think the area on this side is if the whole area is 1? What do you think the area right of the axis would be? Since this is perfectly symmetric, 5, exactly. Oh, that makes sense, doesn't it? Exactly half the results are above average, exactly half the results are below average. But what we do is we say, well, what about between 1 and 2, or between -1 and 0, or between -2 and 1? In other words, any region, the probability of that outcome is equal to the area. Now, this is different than things like a coin flip. Coin flips are discrete outcomes, right? I can get 0 tails. I can get 1 tail. I can get 2 tails. I can't get 1.5 tails. Do you agree? I mean, I can get 0, 1, or 2. Things that are measurements are called continuous. Things that are counts are called discrete. Like how many kids you have, that would be discrete. But how much you weigh, do you have to weigh an integer amount of pounds, or can you be a fraction? Think about that for a moment. Can you be a fraction or a decimal in terms of your weight? Could you be 137.5 pounds? Or in fact, could you be as many decimals as you want to measure? Yeah. In fact, if you ever gotten on a scale, a digital scale, doesn't it give you tenths? So in other words, you don't have to be a whole number of pounds. You can be somewhere in between. A human being can be 180 pounds. They can be 181 pounds. And there's an infinite number of weights in between them. Okay. Height, same thing. So say somebody is 6 feet tall doesn't mean they're exactly 6 feet tall. It means they're probably between 5'11" and a half and 6'1.5" and we just round it to 6. But human heights, between 6 foot and 6'1", there are an infinite number of heights that I could squeeze in there, right? Fractions and decimals. So any form of a measurement is always what we call a continuous thing. We report integers. When you go to the gas pump, I feel kind of naive because my wife was filling our cars up this last weekend. And she mentioned $5 a gallon. I'm like, 5? I just filled up a couple weeks ago. It was like 4.5. And she's like, no, she went to Costco and it was like $5.50 or something. It was something absurd. When did it do that? Well, when you go to the gas pump, what does it first of all say? They'll say 5.399. They give you an extra decimal place. You guys know that, right? It always gives you 3 decimal places for the gas price. Then when you're filling it up, your volume usually is giving you 3 decimal places also. It might say 12.472, gallons. Now think about that. If the gas price has 3 decimal places and the volume has 3 decimal places and you're multiplying the 2 together, that's a 6 decimal place answer. But when you pay, you're not paying, you're only paying to the penny because everything's always rounded to the nearest penny. So rounding happens all the time. That doesn't mean that you can only have this much or this much. You have stuff in between, but in the cost is just rounded to the nearest penny. When you go to the grocery store and you're paying tax on stuff, it's rounded to the nearest penny, but any decimal value is humanly possible. So if there's decimals involved or even fractions involved, we say it's continuous. So we don't say what's the probability a human being is exactly 6 feet tall, because that would be one outcome out of infinitely many possibilities. We'd say what's the probability a human being is between 6 feet and 6'1" or 6'2". Oh, now we'd have an area, we'd have a region, and then we can actually look it up. So today I want to teach you how to look things up. So I'm going to go to the share screen here. Hold on a minute. This is kind of blocked off. All right. Okay, whoops, wrong one. Hold on. Okay, so here's the scary set of numbers that we're all going to be looking at. And I will also bring it up on the big screen simply because I want to show you guys what it is I'm looking at all times. Come on. There we go. Let's see if this is on. If this is on. No. Just one moment. Oh, I'm going to turn these things off. Okay. So let me get off. I'm going to do the same thing that you guys have in front of you. So this is what you guys have in front of you. I didn't want to break the thing, but why would anybody do that? These things are ancient.
Professor, I have that chart also.
Oh, you mean you have a physical printout of that?
It says negative z-scores. I got it out of my elementary statistics.
Oh, great, great.
So I have it.
Then do this. I'm going to take away the share screen if you've already got it. I did this for your benefit. Okay,
Yes, I have it.
That's great. Then let me do this. Let me go back to this. Now, got the same thing up here because I want to be able to make reference to it. Let's see. Let's change the angle. There we go. So something in the background here. Oh, hold on. Let me. So this scary looking table here basically is a table of probabilities. And you notice all of these horrible, hideous decimals. So go ahead and look at the thing in front of you. It's the same thing. All of these horrible, hideous decimals are all 4 decimal places, interestingly enough. But the important thing to understand is the way this is designed, it's if I ask for a probability, let me go back to my picture. It's always the area to the left of the z-score. So as the table moves left to right, it's always the area to the left. So if I'm almost all the way to the end on the right side, does it make sense to say that the area would be very close to 1? And if the whole area is exactly 1, then anything on the far right would be close to 1. What about anything on the far left? Close to 0. And what about anything around the middle? Be close to 0.5. Does that make sense? So when you're looking at the table, so for example, let me go up to the bottom of this page. Wish I had a little more flip. There we go. What you have, these are the z-scores to 1 decimal place. Now look at the top row. The top row is the 2nd decimal place. So this would be negative 2.11, negative 2.12, negative 2.13, and so on. Does that make sense? So you have every z-score to 2 decimal places, but then what are these probabilities? This is the area to the left of that z-score. So let's just pick one at random. Let's say negative 1.82, right? Because I'm in that column. Negative 1.82. Do you see the number on your? You can look at your thing. You see 0.344. That means on my picture, on my curve, negative 1.80 is here, negative 1.82 would be really far to the left, and I'd be giving you that much area. A tiny, tiny bit of area. Does that make sense? Some sense to you? Oh, okay. Now, the nice thing is you don't calculate that area. It's already been calculated. You just have to read it correctly. So I'm going to ask you a question, and we have 2 tables here in front of you. You have negative z-scores, and if you flip the page, positive z-scores. You can't fit them all in the same table. It's just too big. So let's flip the page to the positive z-scores, shall we? The positives. Now this, I don't know why this is still on there. Hold on. There we go. I don't know why I'm still giving me stuff on the side. Bigger screen now. So now I've got the positive z-scores. And again, this picture here is absolutely critical. This tells you how you're reading it. Okay, if I give you a positive z-score, that means I'm to the right of 0. What you're seeing here, these probabilities are equal to the area to the left. So do notice as you go down the table. Now see the z-scores? You don't really get much bigger than 3, do you? It is really, really unusual to have a z-score bigger than 3. Because if the curve looks like that, to be 3 standard deviations above the mean is absurd. That means, for example, if we're talking about human heights, those are probably the people over 7 feet tall. You go, but there's lots of people over 7 feet tall. There's probably hundreds of people over 7 feet tall. You're right. How many people are on planet Earth? Over 7 billion? Oh, 100 compared to a billion. That's not very many. That's 1 in 10 million, by the way. Does that sound rare to you? Oh, yeah, yeah. So if we were talking about human heights, we'd be talking about the people who are extremely tall or the people that are on the other end extremely short. Now, if you were 5 foot tall, would you be considered extremely short?
It depends on who you ask. All my friends make fun of me.
Probably not. You wouldn't be considered tall. You'd probably be considered short, but would you be considered the extreme? No, that would probably be somebody who was a dwarf or a midget, somebody who was by technically, really a hobbit. You're 4 feet tall. Okay, I've taught students who were dwarfs, and they'd stopped growing at around 3.5 feet tall. Lived, very healthy, normal lives, but there's like, where's the rest of the height? And I've also taught students, I've had students who were 7 feet tall and literally, ducking to come in the doorway. I've seen the extremes, but the vast majority of human beings fall into the same range. So what we have the ability to do is say, well, how extreme is extreme? Well, that's what the Z table will tell us, the probability. So let's look here, for example. If I take a Z-score, let's just take 3.0. If I take a Z-score of 3, that means you were exactly 3 standard deviations above the mean. That is hard to beat. Exactly 3 standard deviations above the mean. Right here, 3.00, 0.9987. The probability is 0.9987 to the left. Would you say that accounts for almost every possible value? 99.87% of the values? Yeah. It'd be absurd to be much higher than that. Wow. Okay. So let's do this. I want everybody, because we're going to look at the quiz later on. The quiz, has anyone looked at today's quiz? The one for today's class is just calculating by looking things up. So I'd like everybody here to do, okay, so Rosalind, you have this table in front of you, is that correct?
Yes, Professor.
Okay, then what I'm going to do for a moment, everybody has their own table. So I'm going to turn off the display so I can write on the board. I'm going to turn off the display so I can turn off the display. Wow, this thing is so slow. Okay, so here's what we're going to do. Everybody's going to look at their tables. And let's start real simple. And I'm going to show you the notation, okay? The probability that a Z-score is less than, let's start simple. Let's just say 1.00 is, and here's how we write that statement. We write it like this, okay? We write probability Z less than 1.00. We write it that way. And we always give the decimal places. We don't round Z-scores except to the second place. Because if I said a Z-score of 1.00, that's not going to be the same as 1.01 or 1.02 or 1.03. So we say 1.00 to make sure we're looking at the correct number. So on your table, so first we'll go to the positive Z's, okay? Now what number do you see corresponding with 1.00? 0.8413, perfect. And so we'd write like this. That's exactly correct. So it would look something like this if I have the tail, right? If that's 0, then 1 might be about there. We're saying, remember, if the entire curve has area of exactly 1, 0.84 is pretty good. In simple English, what we're saying is if we have a normally distributed set of values, such as human heights, we know this from experience. Human heights basically normally distributed. You're just as likely to be above average as you are below average, and so on and so on. that we'd be saying about 84% of all the people are no more than one standard deviation above the mean. Does that make sense? That's what that means. By the way, could you tell me what's on the other side? How many people would be above one standard deviation? How would I figure that out? So specifically subtracted from 1. Does that make sense? Oh, this corresponds to that area. What would that be? That would be 1 minus. Ah,
Okay, so just so I'm understanding, I'm looking at the quiz, but
don't look at the quiz yet. Don't look at the quiz yet.
are we,
The quiz,
are we using this for the quiz?
yes, the quiz is so incredibly easy that no human being can possibly miss a question once you understand what you're doing. Don't try to figure out the quiz before you understand what we're doing. Yeah, when we're done going through this, the entire quiz can't take more than a minute. I gave you 10 questions. It really can't take more than about a minute or two if you're doing it correctly, because there's no calculating, you're just reading. But you have to know how to read it. So do you all agree that I looked up that number, but that number would be this, wouldn't it? It'd be 1 minus. Now, I might need a calculator to do 1 minus, but that's what would be here because the whole thing adds to 1. Okay, because the way the table is set up, it's set up always to values to the left, just to make it easier to interpret. But what if I wanted values to the right? Well, then I just do 1 minus because that's what's left. Let's try another one. All right, let's find the probability that a z-score is less than, put a different number now, negative 0.86. What is the probability a z-score is less than? And so then the way we ask that question, we put a negative 0.86. Now, before you even answer the question, it's kind of a common sense thing. What's a 0.86? Can somebody tell me something about my answer? It ought to be less than what? Not less than, well, they're always going to be less than 1, but it ought to be less than. No, that's impossible. It's probability. It ought to be less than 0.5 because it's to the left of center. Remember, exactly half is below 0 and half is above 0. Talking z-scores. A z-score can be negative. A probability has to be between 0 and 1. Oh, does that make sense? It's small. So now when I look that number up in the table, I'm looking up, so find negative 0.86. So go down the column for negative 0.8 and now go across. Okay, does everybody see it? So what number is in the table? 0.1949. And so that's the answer to my question, 0.1949. That's it. The probability that a z-score is less than negative 0.86. Now, negative 0.86 would be below average because it's a negative z-score. The probability of being even lower than that is not very high, is it?
That's all you have to write? It's that easy?
That's all, yeah, we're finding probabilities. That's what we're finding.
Okay.
But we're having to read them. Now, if you have a computer and you know how to do the work, you can do this using Desmos. I was playing with Desmos last night. You can do this using StackRange. You can do this. Problem is, it takes a really long time to master the software, and then you have to know how to do the entering. So one of the nice things, if you have the table, you just read it right off the table. If you have a graphing calculator that does statistical stuff, you can enter this into your calculator. But then you have to learn how to do all that. And that's what I'm saying, that sometimes it's just a lot easier to just read it off the table because you're going to get exactly the same answer. But this one's already pre-printed. That's the convenience of it. And all we want to do is correct interpretation. Okay, so would you say so far that's pretty easy? Reading a less than. Okay, let's do another one. What's the probability? Let me change that number. And by the way, I always draw the picture. Whenever I'm doing this, I always draw a picture so that the answer makes sense to me. Let's now do the probability we are less than, how about 2.59? Now, if zero's in the middle, and remember, we said the curve itself literally is only -3 and 3. It's extremely rare It's extremely rare to have a human being or be anything more than 3 standard deviations in either direction. That's actually really hard. In fact, in many situations, you can't even get that far away. Okay, so 2.59 would be way the heck out here. Tell me something about this answer before we even look it up. It's probably close to what? Probably close to 1. Again, I want that to make sense to you because we said to the left. So now when I look up that number, back to your positive Z chart, 2.59. Rosalind, you want to try this one?
Yes.
What do you got?
2.59 would be 0.9952.
Beautiful. You guys got that? 0.9952. Would you say that's most all possible outcomes? It's 99.5% of all possible outcomes. Okay. Is there a Z-score that will capture 100%? No, there's not. Unfortunately, there's not. That's kind of like saying, is there an income that is the highest income a human being can earn? Or is there a housing price that is the highest? In fact, I like using it in sports. We have a highest paid player in any sport. But does that mean that no human being can be higher paid than that? Or anybody who's a football fan, the highest paid player is whatever quarterback just signed his most recent contract, right? And then the next person who signs a contract is going to be paid more. There is no upper limit. Is there a tallest human being in the world? Yes. But is there a height that no human being can surpass? No. And no matter how tall the tallest person in the world is, somebody could be taller at some point. That's why you can't have 100%, but you can be 99.99%. Does that make some sense to you? Do you remember when we talked about percentile rankings at the beginning of the course? 50 percentile means you're let's just say we're talking about babies and their height. So all of you, when you were babies, I'm pretty sure all of you were babies. I don't know, Lila, never, you were born a grown up, right? But most of you were babies. So when you went to the pediatrician and they measured your height and weight, and they'd say, oh, you're the 50th percentile on height and the 37th percentile on weight. Does that mean you scored 50% on the height test and 37% on? No, it meant that you were taller than 50% of the other babies and you were heavier than 37% of the other babies. That's what that means. Can you ever be in the 100th percentile? Well, you're included in that. So you can't be taller than 100% of human beings because you're one of the human beings that's in the group. You can be taller than 99.999% of the human beings. Does that make sense? You can't be taller than everybody if you're included in everybody. You can be the tallest, but you can't be taller than yourself is another way of thinking about it. So percentile rankings is a similar concept. It's I'm bigger than this. So in this case, when we say the area is 0.9959, that means there are not very many results to the right of this. In fact, how much is to the right of this? Well, 1 minus this is pretty darn small. Would you agree? So now here's the question. What if the question is asked differently? Greater than and more in the same thing. In mathematics, we often say greater than because then I think of the inequality, right? A less than, greater than. No one in inequalities, no one says less than and more than. By the way, although in language we say that, but in mathematics it's easier. Oh, less than goes one way, greater than goes the other way. I'm changing it to greater than. So let's start with this one right here. That means I don't want this. I now want this. We call this the tail probability because as it goes out, those are called the tails. So I'm asking you for the tail probability. So I changed the question to greater than. Here's the problem. The tails do not tell us the greater than, they only tell us the less than. But we figured it out a few minutes ago. What is the answer to this question if I'm asking for the greater than?
1 minus.
It's 1 minus that number, exactly. And that should feel pretty close to an oh duh, in that if to the left is one number, to the right has to be 1 minus because the whole thing has to add up to 1. Yeah. But I'm sure that's where it came from. So 0.0048, that's really, really small. So if I want to calculate a greater than, I still have to look up the less than, but then what do I do with it? I subtract it from 1. So let's do a few greater thans. Okay, let's do another greater than. Let's say I want to be greater than negative 1.15. So in my picture, negative is over here. By the way, the picture does not have to be perfectly accurate. Just make sure you're on the correct side of zero. That's the way I like to think about it. Now, the table gives me everything to the left of this, but I'm asking for the area to the right. So how do we do that? Well, what is the area to the left, by the way? 1251. Does everyone agree with that one?
Yeah.
115, 1251. But that's not my 1251 is not my answer because that's the area to the left. So my answer is 1 minus that. Okay. Another way of saying this, by the way, is saying it's 1 minus the probability that Z is less than, because that's what you just did. You looked up this number, which was the 1251, and you subtracted it from 1, and that gave you what, 8749. So do you see, this is not very complicated. I just have to know, first of all, am I going to the left or am I going to the right? If the question is a less than question, you look up the answer and there is nothing else to do. Agreed? If it's a greater than question, you look up the less than and you subtract it from 1. Because we're on the other side of which way we're going. Let's try one more. What is the probability that we are greater than? Whoops, I erased it. Score is greater than, sorry. Let's say negative 0.02. So in my picture, I'm really close to the middle now. I'm really close to the middle. But before I look it up, should this answer be greater than 0.5 or smaller than 0.5, do you think?
Smaller.
We're going that way though.
Oh, okay.
See, I'm a little left of the middle. I know it's a terrible picture, and I want to go that way. If we used exactly 0, then we know the answer is 0.5. We don't got to look that one up. But I'm a little bit to the left of 0, and I'm asking that way. So probably is a little bit more than 0.5. So let's put that in there. So technically, I'm going to look up negative 0.02. I'm going to look up the area to the left of negative 0.02, which is what?
0.4920.
Does everyone get 0.4920? And I'm going to subtract that. I'm going to subtract that from 1. And that gives me an answer that is just slightly bigger than 0.5 or a half. So hopefully that makes some sense to you guys. Okay, so again, I said next day we're going to actually do problems. So I'm going to give you situations and saying, all right, here's the situation. This is the average. This is the standard deviation. And here's the outcome. Well, we have to calculate a z-score and then we'd look it up in the table. So then the only difference between what we're doing now and what we're going to do next time we actually have to calculate the z-score first. Right now I'm giving you the z-score. Okay. Is the calculation of the z-score complicated? No, it's score minus mean divided by standard deviation. But I do need a calculator for that.
I won't be here Thursday. Is it possible?
Well, can we Zoom?
Yeah, well, I'm gonna be in a CT machine, so probably not.
Well, but it can record it then.
Yeah, can you record it?
Yeah, we can do that. We can do that. This I think is okay as long as I don't use too much. I can't really go left and right a whole lot. I do have, which interesting, last semester I had a student who in one of my upper level classes, he brought his camera. It was some version of a GoPro camera and he stationed it right next to his seat and he recorded my lectures but I don't know how he got the entire width of the room. I mean, there's a little bit of warping on the screen. It kind of makes the room look a little bit curvy, but he got the whole thing without having to ever move the camera. And then he recorded all my lectures and I posted them online, and it was fantastic. So he's doing the same thing this semester in all of his classes. He's now a hero, you know, because now that we're back live and you know, recorded lectures are not that easy to do. He phenomenal work. I mean, the quality of the lectures, you think it professional. So what he did was he recorded them all, put them on his own YouTube channel, and then sent me the link so that I could put all of those on Canvas, you know, without having had to record them myself. I like that. I like anybody being able to go back and look at something. We don't always have that luxury. So we now have the less than and we have the greater than. So I'm going to give you a few problems, and I want you guys to do each of these. The more complicated version we're going to do in a moment, but we're not ready yet. So I'm going to just simply write some problems on the board, and I want everyone to try each of them. Okay. Probability Z is less than negative 1.37. These are coming out clearly. All right. I want to do each of these. So look them up and then we'll compare answers in a moment. It's important that you know exactly when you don't have to do any work whatsoever and when you actually have to do a little bit. Some of these, there's no work. Some of them, there's a little bit of work. All right. Shouldn't take long. By the way, I do want to reuse these tables. So probably a little late now, but I'd ask that you don't write on the tables. It does make it hard to read the numbers if you've scribbled over all the numbers. I do have more though. I made lots of them. So Rosalind, the tables that you have in front of you, are they identical to the ones that I put on the screen?
Yes.
Oh, good, because I got them. They're actually from Triola, by the way. So that's why I did that on purpose, because that was the textbook I used for many years. And every stats book on planet Earth has these in them, but in some books, they're harder to navigate. I like the way Triola does it, everything to the left. And then once I get that, then I know what to do if it's to the right or if it's, you know, the others.
It's exactly like yours. Yes.
Does anybody have an answer? Let's see. Yes. I have many. Yeah. And I missed the first hour. So we're reading things from a table here. All right. So the first one is Z is less than negative 1.37. Does anybody have a number? Hopefully you do.
You're right,
0.0853. Does everyone agree with that?
Yeah.
That was a very, very difficult calculation, wasn't it? No, you looked it up. If you're doing calculations, there's something terribly wrong right now. There should not be a calculation. Now, somebody else. 1.92. The probability, by the way, the Z-score does not equal the probability. The Z-score is how many standard deviations above or below the mean. The probability is the area in that picture. So what's the probability that a Z-score is smaller than 1.92 is equivalent to the area? And in this case, it should be most of it. So does anybody have a number?
9726.
0.9726. That means you're pretty far above average if you're 1.92. Okay. Now, I asked you a greater than. Can you look that up immediately? Or do you have to do something? Yeah, the way I showed it before, this is going to be 1 minus the probability that Z is smaller than 0.46. Now, you don't necessarily have to write that, but it's not a bad idea. So you indicate where the number is coming from. So 1 minus what number? 0.6772. And then that value would be what? Beautiful. So the probability that you are bigger than a Z-score of 0.46, it's not really that high. So that means you're still the majority of the vast majority of the scores are going to be below that number because only about a third of the scores are to the right of that number. And this one, 1 minus the probability that Z is smaller than, which is 1 minus, and that's the thing. The reason I'm writing it like that is so I indicate which one I'm actually looking up. I'm looking up that probability. And so negative, somebody else now, negative 2.43. What do you got, Robert? What's negative 2? What's the probability of being smaller than negative 2.43?
0.00.
0.0075, which gives us an answer of 0.9925. Wow. So that means almost all of the scores are going to be bigger than a negative Z-score that's that big. Question?
I just realized that on the, for example, on the problem solving greater than Z, you can just look for the, like, what you're asking in the other, like, if it's negative, look, search for it in the positive, and then that's the answer.
Oh, okay. So you're saying if I want this, I could look at the negative of the, yes, I can. The problem with that is it won't work on the next thing we're doing, but he's right. That's kind of a clever move. In other words, he said, wait a minute, if I look at the table, let's do it this way. Can you find this probability in the table? Let's work backwards, because sometimes, by the way, we're going to do this next day. Sometimes you'll say, I want a certain probability. What Z-score must I get? For example, I only want to hire the top 1% of the candidates who applied for the job. Have you ever heard of something like that? Or I only want to consider accepting the top 10% of the people who, applied for this school. That means I need to find what Z-score must people be hired at. By the way, this is done every single day of the week in a lot of situations. College acceptances, for example, they'll say, I only want to take this, the top this many percentage. So sometimes I start with the probability and I work backwards and I look up what Z-score does it have to be. So if I'm looking up in the table now, to have a probability of 9925, now I'm not looking at Z-scores, I'm looking at the probabilities on the sheet. So do you see 9925 on that sheet? I see it.
Yes.
Does everyone see it? Find 0.9925 as a probability. Okay. Now, when you find that probability, what Z-score did it correspond to? 2.43. Huh, that's interesting. So according to my sheet, the probability that Z is less than positive 2.43 was, oh my gosh. So being bigger than the negative, and so from a pictorial standpoint, we said take a small Z-score and now calculate the probability that you're bigger than it. That's going to be the same probability as taking the huge Z-score and saying, what's the probability that I'm less than that? That's actually very clever on your part to see that. That will always be true. It will always work if I'm only asking a greater than. Okay, so the idea is to do this problem, this is what we did. But if you can be clever and do this, because that puts you at the other, whatever side you're on, it puts you on the other side. So if I want something going this way, then I go that way. Now, these hopefully were easy. So what you did will always work if it's a greater than, or do what I did, subtract it from 1. That's the safe way of doing it. So far, that's pretty easy. There's a third option. I want to hire everybody who's in the top 10%. I want to reach out and help people who are in the bottom 5%. What if I want everybody between here and here? What if I want people that are between? Like I want everyone who's between -1 and +1 in the Z's. We didn't look at that one yet. This is I don't want to say it's the trickiest one, but it's the one that requires the most. So I'm going to draw you a picture. And I'm going to show you, I'm going to give you some geometric analogies in a moment. So here's my picture. I want, and again, that's always 0. Let's just say I have a number here, I'll call it A, and over here I have a number B. Whatever A and B are. But I want this. I want the between. So I want, what is the probability that A is less than Z is less than B? Does everyone see that's how we write it? Z is between A and B. That's not as obvious, is it? Can I see that number from the table? No, I can't see the answer yet. So I'm going to give you a simple geometric example. Actually, let me just make it simple. Let's say, I'm not going to do that. I have 2 circles, and I want to find the area inside the big circle, but outside the little circle. Does that seem incredibly complicated? You know the area of a circle is pi r squared, so that's not really the thing. How the heck would I find the area between them? Be very specific. Take the area of the big circle and subtract the area of the little circle. Is that kind of an oh-duh? It's like, oh, I gotta come some clever formula. No, how about just big area minus little area will give me the area between. Agreed?
Yeah.
So how am I going to do this one? Find that probability and do what? Subtract that probability. Because when you're looking at probabilities, what are you looking up? The area to the left of B gives you all the way, and the area to the left of A gives you all the way. So if I take the big probability and subtract the little probability, will that give me the probability of being between? Absolutely, 100% of the time. Like I said, you can't look up the answer. You have to look up both things and then perform the subtraction. So it's the same reasoning you just did here. Take the big one minus the small one will always give you the between. All right, so let's do this. Let's write this down. This is absolute. By the way, this is assuming that A is smaller than B. Because if A is not smaller than B, then I've just asked you something impossible. I want all the people that are taller than 7 feet and at the same time shorter than 5 feet. Wait a minute. Is there anybody taller than 7 feet and shorter than 5 feet? No. Oh, what I should have said is everyone taller than 5 feet and shorter than 7 feet. Now I'm all the people that are between 5 and 7, which I think would probably be everyone in the room, right? So what do I do here? This is equal to the probability that Z is less than B minus the probability that Z is less than A. That's what our picture suggests that we do. So it's actually really, really this simple, okay? Any question on this? Because of all of the Z calculations you're ever going to perform, this is probably the most common to say I'm between. We now know how to do a less than, we know how to do a greater than, a between is the only thing left. There isn't another one. That's a good thing. We're looking at every conceivable question that can be asked. So, what is the probability, and I'm going to write it this way, excuse me, that Z is between 0.32 and 1.49. So on our curve, and that's 0. So I'm somewhere, something like this. Is it safe to say the answer should be less than 0.5? No matter what I get, do you agree the answer should be less than 0.5? Because I'm taking a region to the right of 0. I mean, everything to the right of 0 is 0.5. We're just taking a little bit of it, okay? So what are we going to do? We're going to say the answer is the probability Z is less than 1.49 minus the probability that Z is less than 0.32. And those numbers I just simply look up. So let's look those numbers up. Okay. All right, somebody other than Destiny, she's got this nailed. They want to tell me what's the probability that I'm less than 1.49? And Rosalind, feel free to chime in anytime you want.
0.49. So that one, you're looking at that one?
Yeah.
It's gonna be 0.9719.
But that's not my answer, because what would that be? That would be everything from here forevermore. Do you agree? And I don't want everything. I only want this, so that means I would have to subtract that part, which would be 0.32. What's the probability there?
6255.
0.6255, and that gives me an answer of what? 0.3064. Oh, okay, that makes sense, because we said we were expecting an answer that was less than half, less than 0.5. So that answer at least makes sense. If my answer had been greater than 0.5, that would kind of disagree with my picture. There's only two truly terrible answers you can give. Only two. Anybody know what they would be?
No. Not giving an answer.
No. You gave an answer to the probability question. No.
More than one.
More than one
Less than one.
and less than zero. More than one, that's impossible, and less than zero is even more possible. In other words, you can't have a negative answer. But how can I get a negative answer? Subtracting in the wrong order. Oh, because I have two numbers up there and I'm subtracting. If I subtracted out of order, I would get a negative answer, wouldn't I?
It's always gonna be B minus A.
It's going to be the bigger one minus the smaller one. Keep it simple. Now, tell me how I could take this. I just told you how you could take this problem and get a negative answer, subtract them backwards. That's incorrect. And by the way, if you get a negative answer, you don't fudge it and say, oh, let me just make it positive. No. Go back and say, what did I do wrong? Because I can't have a negative answer. How could I possibly get an answer greater than one? Adding. Oh, if I had added these two, my answer would have been greater than one. So are these common errors? They're not terribly common errors, but they are errors that occur. I've seen every error that can possibly be made. I have bad news for you. No matter how creative you try to get and really mess up a problem, I've seen it before. Any error that you think, oh, no one's done this one before. Nah, I've seen it. Been there, done that. But there are two errors that we want to guard against. We're answering a probability question. So it can't be bigger than one, and it certainly can't be negative. Okay. But you see, using those two numbers, I could have messed it up. It's possible to mess it up. We don't want to do that. It's not an option. All right, let's try another one. You guys did a great job on that one. I want probability of okay. Negative 3.20 is less than Z is less than 3.30. In English, that means Z is between negative 3.2 and positive 3.3. Okay, that's what I mean. Between. And if it's a betweener, I have to subtract. So I'm saying here and here, and I want everything in between. So before I actually even looked it up, tell me about this thing. It's probably close to one because there's not a whole lot left, is there? You never have to do what I'm suggesting, you know, what do you think? But I think it's wise to say, you know what? This ought to be really close to one because there's not a whole lot left to the left of here or to the right of here. I've got almost the entire curve under there. So now when you look it up, you'd say this is equal to the probability that Z is smaller than 3.30 minus the probability that Z is smaller than. You notice both of these are less thans because what we're doing is we're saying I'm taking that area and I am subtracting that area. So they have to be, the inequalities have to be in the correct direction. If I put a greater than in the middle of that, that's a different answer. So I don't want any greater than. not in that statement. So let's look up these bad boys. The probability that Z is less than 3.30. That's pretty big. What is it? Anyone? 9995. Yikes. That's almost all outcomes. And now I'm subtracting the probability that Z is less than. That means I'm way out here and I'm going to the left. That's called a tail probability. And what does that come out to be? 0.0007. So this answer is 9988. Wow. So would you say we've captured almost all possible outcomes? Yeah, that's exactly what that means. All right, we're going to take a short break. And when we come back, I actually do want to go through the quiz and give you guys a chance to try some of these. All right, so everybody, let's take a break. Pause the recording for a moment. I forgot to re-record this. So on all of the betweeners, remember, it's the probability of the big one minus the probability of the smaller one, and that gives you the probability between, because when you're doing this one, you're finding everything to its left forever. When you're doing this one, you're finding everything to the left forever. When I subtract them, it gives me the stuff between. That's the only one that you actually have to really do a calculation on. The greater thans, you just subtract from one, or you can be clever. And we figured out another way to do it, but subtracting from one is probably safer. Okay, now let me ask you guys a question. What is the probability in a normally distributed set of values that you are within 3 standard deviations of the mean? That means you're between -3 and 2. Let's do that calculation. What is the probability or within 3 standard deviations of the mean? Got a horn in there. Within 3 standard deviations of the mean. 0.9974. Does anybody else get that number? 9974. That means that in a normally distributed set of values, close to 100% of all outcomes are within 3 standard deviations. Is it mathematically impossible to be more than 3 standard deviations away? No, but here's the thing. If I don't have a huge number of people, let's say I'm working with people. If I don't have a huge number of people, it would be very difficult for one person to be 3 standard deviations away. You'd actually really have to have a very large population to have somebody that extreme. So if we're talking about human heights, 3 standard deviations away might be somebody closer to, 8 feet tall, not 7 feet tall. You'd be talking extreme. Okay. Have there been a lot of 8-footers around? It's pretty unusual, but I think the tallest person in the world right now is probably close to 8 feet. We, always used to have those Guinness Book of World Record, books when I was a kid. And I still remember there was a guy, Robert Wadlow. And he lived in the earlier part of the 20th century. He was 8'11". They're estimating. They don't know for sure because he couldn't stand up. His legs were too weak to support him. So they measured him sitting down. He was the tallest person in the world for a very long time. Okay. But I think he's in the Guinness Book of World Records as the tallest person we've measured in the last few centuries. But the thing is that that's a person who would be way more than 3 standard deviations. Do you know there actually was a person named Tom Thumb? Tom Thumb, that's like a mythical character. He was a circus performer. He was really, really small. I don't know how small he was, but if you look him up, he was like literally 2 feet tall, I think. What's that? It sounds like you're not.
It sounds like a name of someone who's joking.
But he was a famous circus. Now, was his legal name Tom Thumb? Probably not. But he was supposedly the shortest person for a long time. He would be more than 3 standard deviations away because of the extreme nature. But human beings, there's bazillions, literally billions and billions of humans. So to be 3 standard deviations away is quite a bit. In a smaller group, it is actually unusual to even be 2 standard deviations away from the mean in a smaller group. Did you find them? Were you looking up Tom Thumb? How tall did they say it was?
They said 34.
3'4"?
That's not.
Oh, that's taller than I thought he was. A full-grown man, 3'4". And then Henry Wadlow, 8'11". Now, if you took their average, it's just around 6 feet. It's kind of extreme. Okay, so the last two, like I said, I find very interesting because we use the last two often to explain things. Okay, to explain things in depth, to say, this is my expectation, but the majority of outcomes are going to be here. Now, I want to get back to this guy now, because the range rule of thumb is a ridiculously convenient device. It's not a law. It's called the rule of thumb. Okay. Rules of thumb are things like common sense guides. Would you agree with that? You say something's a rule of thumb. It doesn't mean it's absolute. You have to do it this way. But a rule of thumb is a common sense guide. And in probability, it's saying, can I identify outcomes that are probably not going to happen or not going to occur very often? Very unlikely. Okay. Now, you getting hit by lightning today is probably not going to happen, right? It's extremely unlikely. That would be right. It's probably from a probability standpoint, you're not really worried about getting hit by lightning today. But what about getting into a car accident? Is that higher probability? What if you drive during rush hour today? Does the probability go up? Okay. So in other words, things become higher probabilities. So when we talk about range rule of thumb, we're talking about extreme, a little bit more of the extreme outcomes. 2 standard deviations away is not extreme, but it's sort of like the upper or lower level of what we would still consider acceptable, but really far. Okay. Does that make sense? So when you're more than that, you'd say, I don't know. So I asked a question. I think it's on, is it quiz 11? Hold on.
That's quick.
Oh, it's quiz 11. Okay, so now I want to move on to quiz 11, which is the one due next day.
I know, I'm gonna get the rest right.
Yes, I can. I want to do this first though. I want to make sure we're all. And I also want to talk about the exam coming up and our exam prep, because that's very, very important. Okay, now you're not going to make a probability distribution for this one. Why not? We did it on the previous quiz because n is 720. On the previous quiz, n was 5. You flip a coin 5 times, I think we can handle a probability distribution. You flip them, you roll a die 720 times. I don't think I need to do, probability of 0 or 1 and 2 and 3 all the way up to 720. That would be kind of time consuming. So now is where we use the powerful results that we came up last day. Remember, if I know N, P, and Q, then what is expected value? N times P, what's variance? N times P times Q. Oh my gosh, that is so much easier. Now, what is standard deviation? It's the square root of variance. Remember, you're not using variance, you have to take the square root. So the range rule of thumb says it is reasonable, not absolutely required, but it is reasonable that the most of all possible outcomes are going to be within 2 standard deviations of that value. So when we did this in class, remember, we treated it like a plus or minus. We said this number plus or minus. So in simple English, if my mean is 100 and my standard deviation is 10, then we'd be saying 100 plus or minus 2 times 10, right? Because 2 standard deviations. So that's what we did in this case. You got the mean for this and you said plus or minus 2 times the standard deviation. Now that gave you the probable range. That gave you the range that is most likely, your outcome's most likely going to occur within that range. With that, then it makes it pretty easy to tell if something's extreme. Does that make sense? If I'm not within that range, you're saying, you know what? It's not that it's mathematically impossible. It's just that's really extreme. Probably not going to happen. Very unlikely. That's it. That's what the range rule of thumb says. Okay. Now, the last one, I like this one. Did anybody do this one? Do you believe your friend? Your friend said they got 550 tails. And you said that 1,000 coin flips, 550 tails? That doesn't seem outrageous. According to the range rule of thumb, is 550 reasonable, or is that outside the range? It's outside the range. Ooh, it's just a bit too extreme for a fair coin. Huh. Now, do you suppose, does anybody have any coins in their pocket? Do people carry coins anymore? No. Does anybody here in this spot have a coin? Even just any coin? Okay, this is just weird. Nobody has a coin. Okay, just pull any coin. Now, I'm going to ask you a question because we always say things like fair coin. You know, fair coin means the probability of a heads and the probability of a tails we're assuming are exactly the same. Is it possible that that's not actually true? Think of the shape of a coin. You have usually a head on one side imprinted, on the other side you have stuff. Is it possible, because of the way the coin is constructed, that one half the coin is heavier than the other? Do you have it? Oh, I don't want you to break into it. Okay, the point being, if I have an actual coin, is it possible that it's more likely to land heads than tails, or vice versa, just because? Oh, okay. So look at your coin. You tell me, do you believe, just looking at your coin, that it's exactly the same weight on both sides, exactly the same? They have different images on both sides of your coin, correct? So is it possible that one side might be a little heavier than the other? Is that possible? And if one side's a little heavier than the other, which side's going to land face down more often? The lighter side or the heavier side? Heavy side. Have you heard the term loaded dice? Have you ever heard that term in gambling?
Yes, it's a cheating thing.
Yeah, it's cheating. But what does loaded dice mean? Well, if I think of a die, it's a perfect cube. And the weight distribution, remember the dots, think of as being painted on. So it's not heavier, not like a coin. It's perfect, it's a perfect cube. But the weight distribution, imagine that you had a die and it was made of balsa wood, which is some of the lightest material. But in the middle of the die, I put a little ball bearing, like a little tiny marble right in the middle of the die. Now, imagine that ball bearing is a little closer to one face or another face, or can you picture what I'm talking about?
Yes.
If I move it from the dead center of the die towards any one side, then that side's going to land face down most of the time, which means its opposite side is going to land face up. Most of the time, it will no longer be 1/6 for each side. That's what a loaded dice means. I've changed the weight distribution so one side is more likely to land down, so that then its opposite side is more likely to face up. Oh, well, short of cutting the die open, and how the heck would I ever determine whether it was a loaded die or not? How would I ever determine if it's an unfair coin or not? Believe it or not, it's as simple as repeating a probability experiment over and over and over and over again, and then seeing outcomes that are not reasonable. Does that make sense? It's actually that simple. I have a die. I was playing dice with my friend, and it seems like they always kept getting sixes. And I can't figure out why. So we checked it out. It turned out, all 6 sides of the die had 6s on it. There's a Harvey Dent die, right? Now, I find this interesting, and I don't know if it's true, but in the NFL, before overtime, anybody understand? Before overtime, they do a coin flip in the NFL. There's actually an expression. Do you know what it is for for choosing heads or tails? I've been hearing this for most of my life. Tails never fails. Have you ever heard that? That's silly. It's equally weighted. No, actually, statistically, if you go back, because there have been hundreds and hundreds and hundreds of overtime games, and do they use the same coin every time? No, they never use the same coin twice. But tails happens something like 52% of the time. It's not ridiculous, but it's definitely more than half the time tails comes up on the overtime coin flip. Go figure. Wouldn't we expect it to be exactly the same, 50-50? But it isn't. It actually tails is quite a bit more often than heads. So if you're calling the coin flip, now if you ever actually pay attention to the coin flip and actually listen, I think you'll hear tails more often because players have started to believe that that's the case. Now, it's still going to land heads almost half the time, but I just found that very interesting because if you truly believe that tails are going to happen more often, and it was the case, then is it a fair coin? No, because it's not 50-50. Yeah, 52-48, it's not 50-50. So if I had a die in my hand that landed one side face up way more often than the others, then I'd say, I don't think this is a fair die. You see, that's a simple way to actually test these things. So the range rule of thumb is just a ridiculously simple way to say, is it reasonable or is it not? We're not saying it's impossible. I have a fair coin in my hand and I flip it 10 times. Is it possible to get 10 tails in a row? Is that possible? Yeah. Is it very likely? No, it's 1 out of 1,024. But you know what? It's 1 out of 15,000 that you're going to be struck by lightning at some point in your life. So 1 out of 1,024 is far more likely. So you're far more likely to flip 10 consecutive tails than you are to get hit by lightning. Neither one of them have a probability of 0, but we all agree that 10 tails in a row is not very likely. It's very unlikely. So we have a stadium full of people, 60,000 people at the Raider Charger game. See, I was able to get people to do all sorts of probability experiments, for me. So I said, all right, everybody in the stadium, you pull out a fair coin and flip it 10 times. Everybody in the stadium, I got to flip. And I said, all right, how many of you got 10 tails? Do you think any hands are going to go up? Actually, quite a few. Why? Because if it's 1 out of 1,024, but there are 60,000 people, that means around 60 people should get 10 tails in a row. Does that make sense? That's your NP. Oh, it's also called what we said, the law of large numbers. If I know the probability of something, but I do it on a huge scale, what I physically see should kind of mirror what the probability suggests. That's why the NP is so valuable. Okay. So if the probability of 10 consecutive tails is only 1 out of 1,000 roughly, but I have 60,000 people, well, 1 out of 1,000 and 60,000 people, it's 60 people. Does that make sense? So, oh, yeah, it's not very likely, but it can happen. By the way, what about the getting struck by lightning part? I have 60,000 people in the stadium, and it's only 1 out of 15,000 you're going to get struck by lightning in your lifetime, but there's 60,000 people. How many of those people do you expect to get struck by lightning at some point in their lifetime? Exactly, 4. Isn't that crazy? That's how the numbers work. And if you actually followed it and could, watch these people for the rest of their lives, it's probably pretty accurate. Okay, any questions? We're gonna end soon. Rosalind, thumbs up or thumbs down on the Zoom format today?
It was absolutely perfect.
So it worked for you.
Yes,
Okay,
it did.
then if I can remember, I'm old, so memory is kind of an issue with me. If I can remember, I will try to do this certainly for the near future. Destiny had a similar request for next time. Because it's not just that you can follow if you're not here, but then you can rewatch if I can remember to, record.
Yes.
That's not a
Yes.
guarantee that I always remember to record.
I'll remind you, Professor.
I lost some of the middle when we came back from the break. So I'm going to stop now. Okay, now